So I'm going to teach you guys how to use the mole. The mole of a substance is going to be 6.02 times 10 to the 23rd representative particles of that substance. It is the SI unit for measuring the amount of a substance. So actually that's what it says right here, 1 mole, 6.02 times 10 to the 23rd molecules. You can think of a mole as being like chemistry's dozen. So for instance, 1 dozen equals 12 eggs. So in chemistry, 1 mole equals 6.02 times 10 to the 23rd representative particles. Representative. So in chemistry, we use the mole. It's just basically a way for us to represent the amount. It's just a lot easier. Another example of this would be like 1 ream of paper equals 500 pieces of paper. So again, just another example there. So a mole in chemistry is R dozen. So we just use that. I give you guys another example of this. 2 moles then, for instance, equals 2 times Avogadro's number. 2 times alpha A. So we got 2 times 6.02 times 10 to the 23rd. And I get a value of 1.204 times 10 to the 24th. So as you can see, if you got 1 mole, that's 6.02 times 10 to the 3rd. 2 moles, you just multiply this value by it. So 2 times that will give you this 1.204 times 10 to the 24th. It'd be like the same thing as saying if I had 2 dozen, I think you all would agree that 2 dozen is 24 eggs. And what did we do? We took 2 times 12, and that gives us 24 eggs. So if I have 1 mole of something, it's 6.02 times 10 to the 23rd. 2 moles would be 2 times that value. All right. And this number we call 6.02 times 10 to the 23rd. It's called Avogadro's number. I have mentioned that in the slides here. So 6.02 times 10 to the 23rd is Avogadro's number. And that was found by studying carbon. Okay, so let's talk about representative particles because it says it right here. Like, okay, what does a representative particle mean? Well, it's whatever we want it to represent for that particular problem. It could represent an atom, it could represent a molecule, or it could represent a formula unit. I can give you an example of this. So if we wanted to figure out how many molecules of H2O, we could figure that out. So this would be like a molecule. Maybe we wanted to figure out how many atoms are in there. Well, then you would have to go, this would be 3 atoms. Or formula units would just be like your sodium chloride. So there it is. So representative particle is whatever we want it to represent. So here's another example or a table showing you kind of the meaning of a representative particle. So a single nitrogen atom, maybe we want to be 1 mole of that, could be 6.02 times 10 to the 23rd. Maybe we wanted it to be the whole molecule. Well, we can. We can have 1 mole of nitrogen gas would be 6.02 times 10 to the 23rd, which would be that guy right there. We could say water, for instance, that would be a molecule. So 6.02 times 10 to the 23rd. It can represent an ion as well. Let's say we wanted to know how many calcium ions are in a solution. Well, we can have it represented 6.02 times 10 to the 23rd as well. If we wanted it to be a formula unit, that would be like an ionic compound, we can, or the whole molecule as well. So that's what representative particle means. Here is the roadmap on where we're going to be going in chapter 10. This roadmap is going to be a very, very handy resource for you. It's going to help you with your calculations. You don't get to use it on the test, but it is a nice way to learn about how to convert from like a mass to a mole, and a mole a representative particle. This is basically the math we do in chapter 10 right here. So this is definitely a really big slide for you. And today we are going to learn about this one branch. That's it. We're going to learn about how to go from a mole to a representative particle, and to go from a representative particle to a mole. That's all we're learning about. Later on, we'll add this branch in, and then another day we'll add this branch in. So right now, we are focusing on this one right here. Okay, so let's look at an example using that branch. So it says, magnesium is a light metal used in the manufacture of aircraft, automobile wheels, tools, and garden furniture. How many moles of magnesium would be in 1.25 times 10 to the 23rd atoms of magnesium? All right, so here's what you're going to do. For any sort of chemistry problem, we are going to start by writing down what do we have, what's the information we're given. In this case, it's 1.25 times 10 to the 23rd atoms of magnesium. So I'm just going to go atoms of magnesium. Then we figure out, what are we trying to find or figure out? In this case, we are trying to figure out how many moles of magnesium we have. So over here, I'm going to put a mole. All right, so here's where your dimensional analysis is going to come into play. We looked at how to do dimensional analysis in chapter 3. Here's where we're really going to start to use it. So if you have your guys' roadmap in front of you, we're going to go from atoms, which is a representative particle, and we're going to convert it to a mole. In order to do that, we're going to use Avogadro's number. So we're going to go 1 mole per 6.02 times 10 to the 23rd. This is going to be atoms. We can make a note that when we take atoms and we divide it by atoms, that cancels out. It's like x divided by x in math, it cancels out. What are you left with? We are left with a mole, which is what we're trying to do. So you're going to take 1.25 times 10 to the 23rd, and you're going to divide it by Avogadro's number. And I get a value of 0.208, and that's rounded to 3 significant figures. So when you guys are doing your homework on Schoology, you also need to take in consideration sig figs, and that's because this value has 3 sig figs. Our answer in the end should have 3 sig figs, which would be that 0.208, which, if you look at it logically, it makes sense. You have 1.25 times 10 to the 23rd atoms, right? But 1 mole is 6.02 times 10 to the 23rd atoms. So if you look at it, we don't have enough. We have a partial mole, and if you do the math, you'll see that we do. We have 0.208 moles. All right, let's look at another example. Here's one. It says, how many moles is 2.17 times 10 to the 23rd representative particles of bromine? So with any chemistry problem, write down what we're starting with. In this case, 2.17 times 10 to the 23rd, and that's going to be representative particles. And we want to figure out how many moles. So over here, we'll put moles. All right. So this is going to be a one-step problem, so we'll set up our dimensional analysis. Here again, we're going from representative particle to a mole. If you look on your roadmap, you're going to see that it's going to be one step. And you're just going to go like this. 1.0 moles divided by 6.02 times 10 to the 23rd. That's going to be representative particles. You're going to notice that representative particles is going to cancel out. You're going to be left with a mole, which is what we want. I suppose before we calculate it, you can see 2.17 times 10 to the 23rd it's not going to be quite 1 mole. It's actually going to be right around a third. So let's actually calculate it and see what we get. Times 10 to the 23rd. Divide that by 6.02 times 10 to the 23rd. So we actually have, and we want 3 sig figs for this one, so 0.360. We do need that extra 0. So 0.360 moles. So if I have 2.17 times 10 to the 23rd representing particles, I'm going to have 0.360 moles. Alright, so here's just another practice problem for us. We should be getting good at this. This is similar to the other two. So let's just kind of work through this one quickly. We have 2.80 is what we're starting with, times 10 to the 24th atoms. Okay, and we want to figure out, well, how many moles are in there. So over here, we're going to put moles. This is another one of those one step where you just go 1 mole and then divide it by 6.02 times 10 to the 23rd. This case, the representative particle is atoms, so we can just say atoms. Cancels, cancels. So then I take 2.8 times 10 to the 24th, and I divide it by 6.02 times 10 to the 23rd, or Avogadro's number, and I get a value of 4.65 moles. And I do need to say that it is 3 sig figs, so 4.65 moles. So you're just taking your atoms and you're converting it to moles. That's really all we're doing. Let me kind of go back to remind you what we're doing. So those last few problems, we've been taking atoms or representative particles or atoms. So we're here on our mole roadmap and we're trying to get it to the mole. So with all 3 of those problems, we've taken representative particles and we've converted it by dividing by Avogadro's number. That's 6.02 times 10 to the 23rd. So each one of those problems, it was divided by Avogadro's number. Here's another one. I think we will pass on this one because this one's exactly like the other 3. Let's try to find a different one. Here's another one that says how many moles. I think we can pass on this one, or you guys can do that one on your own. Okay, so now let's look at the other part of the arm, converting moles to number of particles. Let's say we have the moles is given to us in the problem, and we have to convert it to the number of particles. Well, then you take your moles and you multiply it times Avogadro's number. So that's going to be this part of the branch. Let's say we're given the amount that we have in moles, and then we're going to convert it to representative particles. You just multiply times this Avogadro's number. Okay, so let's look at how that will work. Let's just say we have propane as a gas used for cooking and heating. It says how many atoms are in 2.12 moles of propane. All right, so just like any chemistry problem, write down what you got. So in this case, we have 2.2 or 2.12 moles of propane, C3H8. And I'm going to write down the whole thing, moles of C3H8. And we want to figure out how many atoms are going to be in the end. So way over here, I'm going to put atoms. Now, I know this is a 2-step problem, and I'll tell you why here in a second. This one is going to take 2 conversions. I'm going to show you the first one, then I'm going to explain the second one. Okay, so the first conversion, we have 2.12 moles. We have to convert that to the representative particle. We're going to use Avogadro's number. So first, multiply it times 6.02 times 10 to the 23rd. And in this case, the representative particle is going to be the molecules. Okay, so I have 12 moles of the whole molecule. So my representative particle is the whole molecule. And I divide by mole, C3H8. So at this step, I have molecules of propane, and I could even go C3H8. However, the question is not asking for molecules of propane. The question is asking us for basically atoms in general. So you got to take it a step further, and you have to look at how many atoms are going to be in there per molecule. In this case, we have 11 atoms per one C3H8 molecule. And I'm going to pause and let you guys think about that for a second. We have 11 atoms per one propane molecule. Hopefully that makes sense. Because there is, right? There's 11 atoms, 3 plus 8, right? There's 11 total atoms per what? One propane molecule. That's what we're going to use right here to convert it. So in this case, it's going to be 11 atoms per one, and then C3H8 molecule. All right, so then this cancels with that, and we are left with atoms, which is what we're looking for. So we take 2.12 moles, multiply it times 6.02, 6.02 times 10 to the 23rd, and then we have to multiply it by 11 because there's 11 atoms per molecule. So in this case, we get 1.4, and with sig figs, we want one more sig fig, 1.40 times 10 to the 25th. So this is kind of a neat calculation. If I have 2.12 moles of propane, I know exactly how many atoms that I burnt. Now, we could stop here. Let's say the question asked for how many molecules. Then what I would do is I would stop it right here, and I would just take the 2.12 and multiply it times Avogadro's number. But this problem asks for how many atoms. So in your notes, you might want to start that and make a note of that. All right. So here's another one. How many moles? We're going to skip that one. Okay, here's another one of those ones that we just did. So this one is asking us for how many atoms are in 1.14 moles of the SO3. Okay, so we're starting with 1.14 moles of the SO3, or sulfur trioxide, as you guys know with your naming chapter. We want to know how many atoms. So over here, I'm going to put atoms. All right. Just like the previous one, I know it's going to take 2 conversions to get there, so I'm going to draw in the 2 conversions. The first conversion is going to be using Avogadro's number. So you're going to have 6.02 times 10 to the 23rd, and that's going to be molecules, I'm just going to abbreviate molecules, of SO3 per 1 mole. So hopefully that makes sense. If I have 1.14 moles of it, and I multiply it times this, now I already know how many molecules of SO3 I have. So at this step, I know how many molecules I have. But just like the previous problem, I want to know how many total atoms though. So with this one, we have 1 sulfur and then the 3 oxygens, so it's going to be your 4 atoms this time per 1 molecule of SO3. So then the molecules of SO3 cancel. You're left with atoms, which is what we're looking for. So then you go through the math. I can give you a reminder with dimensional analysis. If the number's on top, you multiply. If it would be on the bottom, you would divide. In this case, we're going to multiply. So 1.14 times 6.02 times 10 to the 23rd. And then we're going to multiply it times 4. All right. And I get an answer of 2.75 times 10 to the 24th. And that's going to be atoms. So that's how many atoms I would have in 1.14 moles of sulfur trioxide. It's kind of a neat calculation. So all we have to do is know the moles of the substance, and we can do all kinds of different things with chemistry. We can know how many atoms, how many molecules, all kinds of good stuff. Here's a good one. This one's asking us for how many atoms are in 1 mole of sucrose. Alright, so now we're starting with 1 mole. It's 1.0 moles of the C12H22O11. And I want to figure out how many atoms. So again, when you're setting up chemistry problems, write down what you know, write down what you're trying to find. So in this case, we know moles and we're trying to figure out atoms. This one's just like the previous problem. So I know it's going to be 2 conversion factors needed. Okay. The first conversion, take your moles, convert it to the representative particles. So use Avogadro's number. So 6.02 times 10 to the 23rd. In this case, it's going to be molecules per 1 mole of it. Your moles cancel. And at that step, you have molecules. We don't want molecules, we want atoms. In this case, it's 12 plus 22 is going to give us 34, plus 11 is going to give us 46. So in this case, we're going to have 46 atoms per 1 molecule. So then the molecule part cancels, and we're left with atoms, which is what we want. All right, so then you're going to multiply straight across again. So 1 times 6.02 times 10 to the 23rd times 46. And we're going to have 2.7 with 3 sig figs, 2.77 times 10 to the 25th atoms. So there it is. 2.77 times 10 to the 25th atoms. Kind of another fun calculation for us. Let's see here. Well, this one we could do individually with that sucrose. So if I go back to that problem, I could just say instead of the 46, just multiply it times 12 in the end, because it's asking for specifically how many atoms of what? Carbon are in there. So I could repeat the problem. I'm just going to skip that one. Same thing. Here's another one where it's asking specifically how many atoms of hydrogen. So instead of multiplying it times 46, you would multiply it times 22. And I believe you would do the same with that oxygen right there. Okay, so now let me go back and recap on what we've covered so far. With this, the big picture here, what have we talked about so far? Well, today you guys have learned how to take a mole and convert it to a representative particle, and you guys have learned how to take a representative particle and convert it to a mole. Sometimes I like to add this to the mole roadmap. So this would be like, if you have the moles and it's asking you to get to the molecule part, you'd go to here, right? But then we could add one more step. Let's just say we want to know how many, we could say X atoms per 1 molecule. So if you guys wanted to add that with a single arrow, you know, X atoms per molecule, we did that. We took the mole, we converted it to, in this case it was a molecule, and then we took it and multiplied it times, you know, whether it was 46 atoms or 8 or 11 atoms per molecule, whatever it is. So if you guys want to add that to the roadmap, that'd be a good idea. All right. So, I guess if you guys have any questions, you can just ask me on Schoology. The assignment is going to be live for you, so you guys can certainly get started on it.